We'll go over these pretty quick because we went over them in class. This is really as a recap if you weren't here. Um, Question 26 was asking you to rank the capacitance based on what was seen. So you could have put in dummy numbers such as 1 or 2 or 10. I left the variables as C. So in parallel, capacitors add up, so that total capacitance was 3C. In series, because each of them would hold less charge, since both the voltage is shared and then the charge is split, compared to a single capacitor, the total capacitance was C over 3. For 3 and 4, it was a little more difficult. So for 3, I added these two, so I got 2C for the parallel part, and then I had to treat that as a single capacitor in series with this. So 1 over 2C plus 1 over C, and then I had to flip it. That gave me 2/3 of the capacitance of just a single capacitor. Here, these two are in series, so I add the reciprocals of those at first. That gives me a top part of C over 2. And then I add that to the bottom capacitor. It gives me 3C over 2. So my ranking was 2 is the greatest, then 4, then 3, and then the smallest would be 1. For 27, assuming that this capacitor is uncharged just after the switch is closed, the bulbs would be very bright. Both of them would be equally bright because this is a series circuit. So it's a little weird to think of it as a series circuit, even though no charge flows through the capacitor itself, but charge will flow to and charge will flow from the capacitor, so it really does act like a series circuit. Now that rate of charge slows as time goes on and as the plates of the capacitor fill up, so the brightness will decrease with time. As charge builds in the capacitor, the current flow will decrease also. For P40, the equivalent capacitance, I handle these two first. This is kind of similar to question 26. So I get this as a single 12 microfarad capacitor. These two are in parallel, they add up, so that's a total of 37 microfarads. For problem 42, figure out that this is equivalent to 3.5 microfarads. That's in series with a 4, so I handle that with the formula for capacitors in series. I get 1.87 microfarads. To find the charge going through the battery, I need to find the eventual charge on either, not each capacitor, but actually the total capacitance. So my total capacitance is what I figured out in part A, and the voltage is 12 volts. Then I can figure out the total charge that's going to move. That's 2.24 times 10 to the negative fifth farads, or 22 or coulombs, and that's 22 microcoulombs. For problem 49, this is actually really interesting because we had a circuit where we had this switch at A. I don't know why I forgot to label that as B. I will do that. B, maybe can make that a little smaller. Move that over here. And recognize that when the switch goes from A to B, now this whole part of the circuit is not involved. This whole part of the circuit is involved. If the capacitor was fully charged, it would be at 9 volts also, the positive plate being positive, the negative plate being below. So top plate positive, negative plate below. So it's going to act, at least initially, like a 9-volt battery. So 9 volts divided by 50 ohms give us our initial current through here. And this part A would be telling us if it is fully charged, how much charge was on the capacitor. So going from this, parts B and C, we're asking about I think the voltage and current at different times. You would have had to use those time constant formulas we briefly discussed in class, but those are not part of the AP2 curriculum. So again, hopefully that's okay.